Uh, Thank you very much for giving me an opportunity to present a state-of-art experiment at the Asian Physics Olympiad. And I'm choosing the APHO 2016 experiment as to showcase a typical Asian Physics Olympiad uh, experiment. Now, well, this presentation is not exactly a stage show. The stage shows have their importance in initiating students to science as well as enhancing lectures to demonstrate scientific principles. But at the other end, there is the actual act of performing experiments to validate theoretical principles, an essential component of science, since scientific theories have to be validated by definition. The Asian Physics Olympiad is a competition for students of physics who have not entered college. The competition includes an experimental component that tests for various experimental skills. And the various experimental skills that I'm going to talk about, which is tested by a typical APHO experiment, is first comprehension. You can see that that the the question paper itself is 11 pages long. And uh, the question paper is very detailed. It is a holistic amalgamation of theory, experimental planning, execution, and analysis. The student is supposed to go through all this 11 pages and try and understand what exactly is required from them. Another aim of any experimental component is to relate the equipment and terminology used in the experiment. We can see here that again, no, sorry. We can see here again that this part of the question paper tells you exactly what are the equipment that has been supplied and a photograph of each of these components out here. Students are supposed to identify these components and then follow the instructions follow the instructions to set up the experiment. Well, every experimental problem in APHO is usually an analog of a research problem, which can be handled by a school student of class 11 or class 12. The APHO 2016 experiment is an optical analog of a reflected high-energy electron diffraction phenomena of a nanostructured ZnSe surface that has a periodic lattice spacing uh, and a non-uniform 1D modulation on the surface on a nanoscale. So you can see that these are reflected spectrums or diffraction spectrums of the ZnSe, which are shown in these photographs out here. Now, the aim of the experiment is to understand this phenomena with an optical analog so that we can uh, so that we can actually do things on a micrometer scale and therefore is handleable. Now, as I said, we follow the instructions given from pages 2 to 5 to set up this thing out here. One can see that there is a circular scale out here. There is a place where the sample is to be placed, a laser diode out here, which is at an angle, tilted at an angle theta, making sure that the light always falls on the center of the sample. And phi is the angle that the grating elements make, grating scratches, for example, make with the z-axis. This is the z-axis. Now, there are 5 samples given in this experimental test. Each sample is a square of dimensions 1.5 by 1.5. Each of these is placed on placed on a holder whose dimensions are 2 centimeters by 2 centimeters, and there is a mark out there which which coincides with the zero mark on the circular scale. So when we put the sample on the table, this mark, one has to be careful that this mark is coincides with the zero of the circular scale. Now, another very important uh, part of an experiment is data collection. And data collection is an art. Remember, there is a time limit on the students to complete this experiment, which includes reading the stuff, setting it up, and performing the experiments. So, and performing the experiments, collecting data, and analyzing data. Now, it is expected that the students can carry out a judicial mixture of procedures and innovation so that he can manage the data economically. Another important part of all data analysis is trying to linearize data. Why? Because whenever the data can be linearized, then of course straight line graphs reveal interdependence of variables and display valuable information. Plotting a straight line graph is much simpler than plotting curves. And of course, the last part of any data analysis it would be to realize the limitation of the experiment in terms of least count of the instruments, systematic errors, random errors, and effective averaging techniques to minimize statistical errors. As we go on, we shall see that judicial questions are asked or questions are posed judiciously so that all this pedagogic aims of the experimental component of an APHO experiment is met. Now, well, we start with the experiment. Sample one is a plane mirror. The laser is adjusted so that the spot falls on the center of the sample. The reflection is seen on a graph paper placed at a fixed distance of 15 centimeters. That is the distance from the center of the sample holder to, to the graph paper. I'll just show the way that we set up this experiment. Here we go, trying to get the laser at 30 degrees. I'm trying to adjust the laser so that we get a spot right at the center, and then it is reflected onto the graph paper out here. This is going to be the this is also going to be the 0th order diffraction diffraction I mean the 0th order of the diffractions that we'll get from other samples out here. The task is to obtain the laser tilt angle theta. Let me be honest, even though we have performed these experiments, I'm picking up data, I'm picking up answers from the model answer sheet so that you get a feeling, or students get a feeling of how the various skills involved are marked in this paper. So the height, age of the reflected spot is measured, and the distance from the center is given is 15 centimeters. From this, we evaluate theta is equal to 10 inverse this. Let me just zoom in this and show you the. All right, this is about 5.5 centimeters, and so we have the theta to be 20.1 degrees. There's a note here which says that in the various experiments, theta can be between 19.7 and 20.3, and these are all allowed values. So, all right, data from sample 2. Sample 2 is a steel plate etched with straight, non-uniform grooves parallel to the two edges. Task is to obtain the diffraction patterns and plot them on a graph for phi equal to 30 degrees, 0 degrees, 30 degrees, 60 degrees, and 90 degrees. And this is an actual experimental result. You can see that there is a continuous graph out here. It's circular kind of a pattern. Then for phi equal to 30 degrees out there, phi equal to 60 degrees out there, and phi equal to 90 degrees is a straight line. But notice that all this seem to be a continuous kind of a pattern. Now, the task involved with this is to record the diffraction pattern onto a graph paper for phi equal to 30, 60, and 90 of the rotation, and write down the corresponding angle of rotation. So here it is done: phi equal to 0, phi equal to 30, phi equal to 60, and phi equal to 90. Sample 3 is a still plate edged with straight uniform grooves spaced parallel to the two edges with spacing A. Task is to obtain the diffraction patterns and plot them on a graph for phi equal to 0 degrees, 30 degrees, 60 degrees, 90 degrees, and calculate the spacing A and the mean and standard errors. Now you can see that the pattern of the graphs are exactly like those in sample 2, except that right now we do not see a continuous kind of a graph. What we see are bright spots out here. Yeah. Yeah. This is for phi equal to 90 degrees, 60 degrees, 30 degrees, and phi equal to 0. These are plotted on a graph. The tasks, the data from sample 3, the task attached is to mark the centers of the diffraction spots from sample 3 for phi equal to 0 onto the graph paper and write down the corresponding angle of rotation phi next to each. So here it is written down: phi equal to 90 degrees, phi equal to 60 degrees, 30 degrees, and 0 degrees. The theory of the diffraction patterns from sample 3. Well, basically these are reflection gratings. So whenever the path difference between 2 points is for reflection from 2 different points of the same groove, or adjacent grooves satisfy m lambda is some multiple of the wavelength lambda of the given light, which is of course given 650 nanometers. One can actually get into these conditions out here. This a relation between y squared and this out here. For detailed derivation, one can refer to this paper, which I have quoted here: Reflected Diffraction from Linearly Patterned Surfaces. There are 5 authors there, or 6 authors. This is American Journal of Physics, 86-9, September 2018, pages 690 to 700. So, as is evident from here, if phi is 90 degrees, then of course x is equal to 0, and therefore we get a straight line for various y's. Y satisfies this equation. If we place x there and etc., do a little bit of algebra, and y is exactly equal to this. And now the tasks. It is said that rearrange the thing so that you can write it down as sum in terms of the grating constant A, write it down as a quadratic AA squared plus BA plus C equal to 0. And after doing a little bit of algebra, you are asked to identify A, B, and C. And you can see how the points are distributed out here for the calculation of such things. Now, so you take the measured values of y, order 1. Remember the 0th order, we know where the 0th order is. And from there, we measure m equal to 1, m equal to 2, m equal to 3, and so on and so forth. And from there, remember, the equation that we have is a quadratic, and therefore A has 2 possible values. And let me blow this up. You can see that if you look at A1 calculated, they are roughly a constant. Whereas A2, there's a lot of variation out here. Therefore, A2, it is given that the grading constant is a constant. I mean, they are uniform spacing, so we do not take the A2 value and we sit down and calculate from there. Okay. And then uh, calculate the mean for the grading constant A in meters to 3 significant figures. And so A1, since we have 6 values there, the mean of the grading constant A can be evaluated by this, and the standard error from is this. So the main grading constant is this much, and the standard error is 8 times 10 to the power minus 8. And you can see that the total tasks is given 0.8 points, and you can see how they are distributed to get the things. Out here, you can see that if the uncertainty in A is within 10%, 10%, then you get full marks. If it is within 20%, you get 0.1 marks, and otherwise you get 0 points. So you have to be very careful. This calculation itself would tell you how careful you have been in measuring your data and how skillful you have been in obtaining the diffraction patterns. Well, that was the task with this. Sample 4 is similar to sample 2, but the non-uniform scratch grooves are at an angle phi star with reference to the 0 degrees, 180 degrees mark of a circular scale. This is an actual data. When we are at 0 degrees, you can see it is no longer circular because there is a certain tilt and therefore the 0 mark is not exactly the lines are not parallel to the 180 mark. So what you do is along the continuous diffracted graph projected on the graph paper, measure the coordinates in centimeter for 10 points starting from -1 centimeters to 35. Enter your results in the corresponding table. And this is done out here. You can see there's a range of values that you can go out there, okay? And from there, you can sit down and you make this table out here. Now, you can, based on the equation 1 given in task D, which was construct a linear equation in the form, this is called linearizing the data. Okay, and let me just zoom this a bit. And this is the kind of a thing that you are supposed to linearize the data on. So that if you, just a little bit of rearrangement and etc., and you should be able to find that mxyd is equal to this, and f is this, and s is 10.5. So plot this. Now, if you plot m versus x, then of course the slope will give you s phi, and this will give you d. This will give you fd. Okay, the intercept. So again, the data are picked up from the model answer sheet. Now, this is the linear plot, and then you look at phi equal to 23.2 degrees. Well, you have been asked to do this, and therefore you have to do this. But there would be a very simple way of getting the thing. You turn the sample till you get a straight line. So if you get a straight line, remember, when do you get a straight line? When the sample, the gratings are at 90 degrees to the incident beam, right? There. But this is not going to coincide with the 90-degree mark of the circular scale. Obviously not, because there's a tilt. The difference in that would exactly give you what is phi star, and therefore phi star is just 23.2 degrees as you get from there. Sample 5 is a steel plate that has non-uniform scratch grooves as well as grooves with uniform spacing perpendicular to the non-uniform grooves. Task is to obtain the diffraction patterns and plot them on a graph for phi equal to 0, phi equal to 30, phi equal to 60, and phi equal to 90. You can see these graphs, right? You can see these graphs. Phi equal to 0, you can see that these are circular things, but you see a lot of them out there. And you can see that the uniform spacings that you have, they are right now at 90 degrees, and therefore the bright spots out here. Similarly with this, right? When when phi is equal to 30 degrees, uh, when the non-uniform scratch grooves are at 30 degrees, then of course the other ones are perpendicular to that, and so they would be at 90 degrees, right? And this is at 60 degrees, and this is when the non-uniform grooves are at 90 degrees to the thing. So these are plotted out here. These are plotted out here. These are the points that you see, okay? Okay, these are continuous graphs out here, and okay. So, well, now you have these two gratings, right? So one is a non-uniform grating and the other is a uniform grating, and they are at 90 degrees to each other. So the pattern that you are going to see is actually uh, a convolution of the patterns of the two things, right? And with that, the distance that you see, if you remember the graphs that we had, uh, okay, the graphs enter the value of b from the graphs that we had. I'll just go back 2 slides and show you that. These, this will be a measure of b, right? Okay. So from there, you sit down and you rearrange this equation like this at phi equal to 0 degrees, and from there you calculate b to be 2.21 times 10 to the power minus 5 meters. So you can see it is a very novel research problem, which has been turned into a very interesting problem which can be handled by students of class 11 and 12 and make them understand the physics behind the patterns that we saw in the zinc selenium structure. Well, that is about it, and thank you very much for this opportunity to enable me present an example of an experiment from APHO. Hope this motivates students to explore and enhance their experimental skills. Thank you very much again.